Hello, so today we are going to take a look at this problem called partitioning into minimum number of Deci-Binary numbers. So what this problem asks us to do is that if we consider a Deci-Binary number to be a number where each of its digits is either 0 or 1, right? And then, for example, 101 and 1100, those two are Deci-Binary, but 112 and 3001 are not because they have digits. They have other digits, right, in them. For example, so like 512, that's not Deci-Binary either, right? And we get a string as input representing a positive decimal integer, just 43, 54, something like that. We want to find what's the minimum number of positive Deci-Binary numbers that we need to sum up to get n. So how many Deci-Binary numbers with this Deci-Binary definition we need to sum up to get n. So if we take an example 43, well, we can subtract first 11, we get 32 back, then we subtract 11 again, we get 21, 11 again, we get 10, and then 10, we get 0. So I'm doing it here in subtracting way, but what this means essentially is that if we do 11 plus 11 plus 11 plus 10, this will give us 43, right? But you can see how I did it like just manually. So we need 4 numbers to get the result. Okay, so this is the problem. Now let's see how we can solve it. Okay, so let's see how we can solve this problem. So let's start out with the first simple example. Let's start out with just one digit, right? So let's say we have just 3, right? So with 3, we know we need 3 numbers, right? We need 1, 1, 1, right? So that we can reach 0, basically, which means that this sum here will give us the number, right? So what you can see here is we kept subtracting until we got to 0, right? Similar thing, if we take another one-digit number, 4, well, we need 4 ones, right? And so 4, right? Now, well, let's step it up a little bit. Let's say we have 12. How many we need? Well, we need to do 1, 1, 11, right? So that we can, and then here we will reach 11, that would mean 0, 1. And then we'll need 1, 0. Of course, we can delete this leading digit, right? And that will give us, right? That will give us 0, 0. So what we need for 11 is just 11 plus 0, 1, which give us 12, what we need for 12, right? So the result here is 2 numbers, okay? Let's just do more just to see the pattern. So let's say 24. What do we need? Or 42. Let's do 42. So for 42, well, we definitely need 11, and that will give us here 31, and then another 11, that will give us 20, right? And then we do another 10, that will give us 10, and then another 10, right? And that's pretty much it. So it's 11 plus 11 plus 10 plus 10. And then this will give us 4. So you can see a pattern here, right? So here we needed 3, here we needed 2. Let me just put this back here. So here we needed 3, here we needed 2, and here we needed 4. I can do more examples, but you can notice the pattern is that every time we just need the max number of the number, right? Why is that actually? Because you can see here, if we have 42, right, we can use 1, 0, but that's not the optimal solution, right? Because, well, we can just replace this with 1 and we'll be better off, right? But we won't stop unless we get 4 down to 0. But to be able to get 4 down to 0, we need 4 numbers, right? And so let's take maybe even more complicated example just to make this more clear. So if we take, let's say, 8, 1, 7, 5, 2, right? Let's take this number. So what do we need? So we are always better off taking 1, just putting 1 whenever we can, right? Because if we let's say put 0 here and we can't take 1, we can put 1. Then we would have to have another digit, another Deci-Binary number just to get rid of this one, right? And so we would have used two Deci-binary numbers instead of just one, right? So instead of just doing, let's say, this, right? We are better off just putting ones whenever we can, right? Because otherwise we will need to put another one, we'll need to put another 0, 1, 0, 0, 0 to get rid of this one, right? So it makes sense to always put as many ones as we can, right? So, as we can. And the other thing is that, well, we need the highest number to get down to 0, right? To get down to 0. But along the way with doing that, we can just cancel all the other numbers, right? So essentially the solution here is, in a greedy way, is just like the max digit in n. This is the actual solution. Okay. Okay, so let's try it on this example here. So what would it look like? So with this one, well, we can just put as many ones as we can. So all of them, since none is 0. So at this point here, we would have 7, 0, 6, 4, 1. And then we can put another one. So now we can put 1. For 0, we can't. We reach 0 here. So we need 0. And then 6, we can still put 1. 4, we can still put 1. And 1, we can still put 1. Okay. So after this, what do we get? We get 6, still 0 because we put here 0, 5, 3, and here we have 0 now, right? So we again put 1 where we can. So 1, 0 here for this one, 5, still can put 0, 3, we can put 0, 0, let's put 0, right? Because we can't take anymore. Okay, so now here we have 5, 0, 4, 2, 0. So we go again, do the same thing. 1, 0, 4, 1. We can for 2, 1, 0. So here we get 4, 0, 3, 1, 0. Right? So you can see here, this biggest number is what's driving. We'll keep putting 1 until the biggest number gets to 0, right? At that position. And so here again, let's just keep going so we can make sure we understand this. So 0, 0. So now this one got to, sorry, this is the number actually I need to put here. So here we can put 1. Here we can put 0. 3 we can put 1. 1 we can put 1. 0 we have to put 0. So now we get to 3, 0. So you can see every time we subtract by 1 from each digit, that is not 0 yet. And then again, 0, 1, 0, 0. Right, so now we got 2, 0, 1, 0, 0. So you can see the main thing is this has to get to 0. The biggest number, which is 8, has to get to 0. And then 1, 0, 1, 0, 0. And now 1, 0, we are close. Now you can see what's left is just the highest number. And so we just do 0, 0, 0, right? And now we are done. And you can see here how many we have. Well, 1, 2, 3, 4, 5, 6, 7, 8, right? So the highest number, and it makes sense because you can see we got from 7 to 6 to 5 to 4 to 3 to 2 to 1. So the goal here is to get the highest number to 0, but along the way, those that have not got to 0 will keep subtracting because we'll keep putting 1. And so this way, we know it's just the max digit in n, because we will always put as many ones as we can for the other smaller ones. And then the highest one, we can't stop until we get to 0. And so the other thing is also the max we can have here is 9, right? Because digit for one digit, the max you can go to is 9. And so yeah, that's pretty much it. Cool. So the solution is just the max digit in n, and it's kind of a greedy solution because we are relying on that we are going to pick the highest Deci-binary number that we can subtract. So that's the main idea there. Okay, so let's just solve it. So let's call this function partitioning minimum or something like that. And then let's say we get n as an input. And so what we need to return is just the max digit. And so this is a string. And so we just need to return max. So So the solution is pretty simple, and mapping n to integer, right? And we can just return this. So we map the string to integers, and then we just take the max. So very simple solution here. The main thing is to get the idea behind it. Okay, so let's run it on an example and just make sure it passes test cases. Okay, so let's see here. So yeah, pretty much just getting the max of the digits here, and just running it on some examples. So let's run the test cases, and all of them pass. You can test it on more, but it should work fine. Yeah, so that's, and in terms of like time complexity, we are just taking the max of the strings here and mapping them to ints. So it's just O of n, O of the length of the string, essentially. Yeah, so that's pretty much it. And in terms of space, it's O of 1. We are not using any extra space. So yeah, that's pretty much it for this problem.